Jnanam Paramam Dheyam. Knowledge is supreme.
In the last couple of lectures, we have been studying Galois groups of some examples of field extensions, which are Galois extensions, and particularly last two lectures we have spent on studying roots of unity in a extension of Q and also in a extension of a finite fields. So just let me roughly recall quickly that what we studied was, given any integer natural number n positive, then we were studying this equation, roots of this equation x power n minus n. So we have two cases, either characteristic zero case, that is, think of this as a polynomial in Qx, that was the case 1, or think of this polynomial in the finite field with Q elements. And then we considered in both the cases, in the first case the splitting field, that I have denoted by Q upper bracket round bracket n. This is a splitting field of this polynomial over Q. We have checked that this is a field extension of degree phi n, where phi n is Euler's phi torsion function, and the Galois group of this extension is isomorphic to the unit group of the ring of integers modulo n. This is what we proved, and this is we also in between proved that this is a Galois extension. So in this case the Galois group is actually the abelian group. It's an abelian group of order phi n. This group we have identified it as the roots of unity in Qn. This group is cyclic group of order n, and automorphism group of that cyclic group is precisely Zn cross. This is what we have used the identification. So that was a characteristic 0 case, and characteristic P case, we know that if you have a field with Q elements Fq, and we had to assume now without loss we could assume this n and this Q or P characteristic, this is co-prime. Q is a power of prime, Q is P power E, P is the characteristic, and then we are looking at the splitting field of this polynomial x power n minus 1, x power n minus 1, and this polynomial is now has simple roots because we are assuming this condition, and therefore this extension is a Galois extension. This is Galois, and we already know finite extension of a finite field is always cyclic. So this is Galois extension with Galois group cyclic. This is cyclic, and this is only a subgroup of Zn cross. So the order of this Galois group, we computed the order of the Galois group, which is also order of the field extension. This order is precisely the order of the integer Q in the group Zn cross. So that is also I denoted by order of Q in mod n in a multiplicative group. So we have fairly good understanding of these field extensions. Now I want to go on further, little more intricate results which will tell us about which groups occur as a Galois groups. This is still vague. I will make it more and more precise when we go on, and we want to therefore extend or do more finer study about the Galois correspondence. So let me recall quickly what is the Galois correspondence we did. So this was the main theorem, that was the fundamental theorem of Galois theory. So that I will abbreviate always, as I said earlier also, FTGT. This is the fundamental theorem of Galois theory. And what we proved was, when we have a field extension, we did it only for finite field extensions. And if time permits in this course, I will go on to more general field extensions. Not even, I don't even want to, I will assume that it's a algebraic extension, not even finite, etc. But that will come probably at the end, or if not, it will be in a further next course. Alright, so we have a field extension L over K, finite field extension, and remember we called it Galois extension. That was the definition was, this was the definition, that was the degree of the field extension equal to the order of the Galois group, Gal L over K. In general, the degree of the field extension is bigger equal to, but when the equality holds, we call the extension to be Galois extensions. We also proved that, so this is the equality when, that is when you call the extension to be Galois extension. We have also checked that this is equivalent to saying that the fixed points of the natural action on the Galois group on the field L, this fixed point is a base field. This is also we have proved. So this is purely a numerical condition, that order equal to the degree. This is not numerical condition, but it is it involves the action of the Galois group. So the whole Galois theory centers around studying the action or operation of the Galois group on the field L, and this is a very natural action. So the action is given by, if you have an element in the Galois group sigma and element in the field L x, that goes to sigma evaluated at x. And as you see, I will today also study this action more carefully, not just basics, but I will go a little bit more deeper. So what is the Galois correspondence? Galois correspondence, so this is, I will keep referring this to Galois correspondence. These are the bijections between the intermediary fields of L over K. That means there are subfields of L which contain K on one side, on the other side the subgroups of the Galois group. These are the subgroups, and we have given the map, one in this direction and the other in this direction. So this map is if you have a intermediary field M, then you just map it to the Galois group of L over M. This is clearly a subgroup here, because these are only M linear maps and these are all K linear maps. So this is a subgroup here, so it makes sense. And this map I have denoted by, let us call today just G L dash, and this way map is a fixed map. So this map is a fix, so that is given any subgroup H, we mapped it to the fixed field of H, which is a subfield of L. Clearly these are all fixed points of all elements of H. So this correspondence we have checked that they are inclusion, reversing, they are bijections, and not only they are bijection, they are inverses of each other, inverses of each other. Now, for example, now this also shows that I am going to ask more questions regarding this correspondence. So, for example, I know if you have intermediary field, then we can talk about its degree over K, Mk, and also we can talk about this subgroup H. This is H, this is H. So, what is the relation between the degree of M over K and H? So, it is easy to see that this one will correspond to the index of the subgroup H in the Galois group. This we have, this is index, this is this double dot H. This is the index of H in the subgroup, in the bigger group, Galois group of L over K. They correspond to each other because we know that this is easy. Let me just write the proof here in one line. We know because L over K Galois, L over M is also Galois. This we have checked. Degree of L over M, this is equal to cardinality of the Galois group of L over M, and degree of L over M and degree of L over K. What is the relation? Degree of L over K, this is degree of L over M times degree of M over K, and we are interested in this number. This number I know, this number also I know, this is cardinality of Gal L over K, and this is cardinality of L over M, and this is what we want. So, therefore, the degree of M over K is nothing but the order of L over K divided by order of L over M. This is precisely the index of L over M in the group L over K, Galois group of L over M. But this is what the correspondence is, this is the corresponding group H. Therefore, what we noted is when you have intermediary field and the Galois group, the information about M, particularly the degree of M over K, that is the index of the Galois group of L over M in Galois group of L over K. So, we have this extra information. Now, I want to also ask questions. If H is some special group, some special subgroup or subgroup which has a special property, for example, H is normal, then what can you say about that intermediary field? How do you read that normality of a subgroup in terms of the intermediary field? Or conversely, we don't know in general. In general, it is not true. We will see by example that M need not be Galois extension of the base field K. All we know is L is Galois over M, but we don't know whether M is Galois over K. And in general, it is not true. We will see this by examples. But then we can ask when exactly M over K is Galois extension. So, that in terms of the group. So, we will check, we will have some results which connects group theory and intermediary fields in a more intimate way. So, right now I want to assume, so the result I am aiming at, suppose H is a subgroup of the Galois group, Gal L over K, and we assume H is normal. normal in G Galois group of L over K. So in general, we will have to, I will recall, in general let us recall, if G is a group and H is a subgroup, when do you call a subgroup to be normal? H is called normal. So we have given a subgroup H, so we have given G is a subgroup of G, and we have given the cosets. So left or right cosets, we will concentrate on the left coset. So this is the set of left cosets. And one would like to know, when will the G by H, the set of cosets, when will it be a group again, in such a way that we have a natural quotient map here. This quotient map is very clear. Any element G in G, that goes to the coset of H defined by the G, GH. All those G times H, as H varies in the subgroup H. So this is the quotient map. So we would like to know, when can we put a group structure on the cosets, so that this natural map, this canonical map, let us call it pi, when this is a group homomorphism. And that is if and only if, what do we know? We get the group structure here will be nothing but GH times G prime H. This will be defined by G prime H. And if you want to define this, we have to check that this definition is independent of the representative G and G prime of these cosets. But that is equivalent to saying the subgroup H is normal. So this is well defined. That is if and only if H is normal. When you want to write down this more precisely or more transparent way, that is equivalent to saying, so equivalently, H is normal in G if and only if for every element G in G, the conjugate subgroup HG G inverse is H. Then we say it is normal. So many people will take this as a definition. So this as a definition, but that is equivalent to what I said, that is more appealing, saying that when will the quotient set will be a group in a natural way, so that the quotient map is a group homomorphism. So that is normal. Now our problem is the following. We have a subgroup H, which is, and normal subgroup is usually denoted by this notation, this instead of only this. So H is normal in the Galois group, normal, and I will prove that this normality is equivalent to saying this H corresponds to the intermediary field M. So this H, so that is fix L, this is our M, this is Galois over K. So that means under the Galois correspondence, normal subgroups will correspond to Galois subextensions. That is the theorem we want to prove it. And obviously this involves studying group actions more intimately, and that is what I want to digress. What is this condition? When will this H be when H is normal? What happens to the fixed field? That is what I want to analyze now. So this is a digression on the group actions. So this is digression on group actions. And we will apply these results to our situation of the field Galois field extension and the subgroup of that. This is what we are planning to do it. But before that, we will understand little bit group actions in a more detail. So let us take in general, let X be a G set. That means, you remember, that means X is a set and G is a group and G is operating on X. So the operation is a fixed operation, that is written like that. Any G in G, comma X, that goes to the element Gx. This is our notation. So this is the operation of the group G on X. Whenever such a thing is given, and suppose H is a subgroup. H is a subgroup of G, and suppose H is normal. That is given to us. All right. Now what do I say? And let us denote also the set fix Hx. These are only the fixed points of X with respect to H. That is, these are all those points X in X, all those elements X in X, such that Hx equal to X for all H in H. These are the fixed points with respect to H. And I will also denote this fixed point set by X power H. This is not a good notation, but today I will denote this. When there is no confusion, we will denote this. Otherwise, we will usually denote it by this. So X power H. So this is a subset of X. All right. So first observation I want to denote is, so observe that. So let me write it as the proposition. So proposition with the notation as above. The first one, X power H is invariant under G. What does that mean? That means if I take any element of G and apply it to any element of X power H, then it will come back again in X power H. So that is for every sigma in G and every X in X power H, sigma of H again lies in X power H. All right, let us finish off the proof now only. So that means I want to prove this. So I want to prove this means what? This is what to be proved. So that means given any element, that means this element sigma X is invariant under all elements of H. So that is to prove, if I take any tau in H, tau of sigma X should be sigma X only. This is for every tau I have to prove. All right, but tau is in H and we are assuming, remember H is normal, that is what we are assuming, H is normal in G. So tau is in H, but H is also same thing as the conjugate subgroup this. So therefore every tau is also an element of this. So that is tau I can write. So that means I multiply by sigma from this side. So that is tau sigma belongs to the coset sigma H. So that means tau sigma will be an element of this coset. So that will look like sigma tau tilde with tau tilde belonging to H. And now what do I want? I want to check this element is sigma X only. This is what we want to prove. So start with evaluate these both sides on X. So tau sigma evaluated at X, this is what we are interested in. This is same thing as sigma tau tilde evaluated on X, but this is sigma of tau tilde of X, but tau tilde is in H and this X was element in x power h, that means x is invariant under all elements of h, in particular of tau tilde. So, this is sigma of x. This is what we wanted to prove. So, we have proved this. So, that means we have proved that x power h is invariant under G. This is a subset which is invariant under G. So, that means this G operates. So, therefore, G operates on x power h by restriction. Of G operation on x, that was given to us, and I will restrict that G operation to x power h. That means we have a map from G cross x power h to x power h. That means any sigma comma x, that goes to sigma of x. This makes sense. That is what we have checked in 1. But I want to say something more. Now, this operation will give you an action homomorphism. That means we have a homomorphism. So, this will give us a group homomorphism from G to the permutation group on this set x power h, bijections. And therefore, we want to know what is the kernel. So, this is the theta map, and we want to know what is the kernel of this group homomorphism. So, this second, this says something about the kernel of this group homomorphism. So, kernel of theta, because it is a kernel of a group homomorphism, it is a normal subgroup. So, this is what is the kernel by definition? All those elements sigma in G, such that sigma, when I send it here as a map from x power h to x power h, that should be identity map. So, we have restricted these to this sigma restricted to x power h is identity map on x power h. That is precisely the kernel of this group homomorphism. This is a norm, and I want to call it h tilde. So, this is a normal subgroup of G with h is contained clearly in h tilde. This is also clear, because to check that elements of h are contained in h tilde means that every element h in tau in h should, when I restrict it to x power h, it should be identity on x power h, but they are all elements of h. So, they keep all these guys invariant. That means on that subset it is identity. So, this is very clear. Now, what is more important I want to say is, when will exactly this kernel be equal? So, that is the statement third. H equal to h tilde if and only if G by h. Now, G by h makes sense because h is normal. This operates faithfully on x power h. All right. So, that is very easy to check, but I want to use this. When will this be equal? That is when it is operates. Both ways are clear. That is essentially when do you say group operating faithfully on the set, that means that the kernel is trivial. So, I want to use this information to our situation in the Galois field extension case. This I will do it after the break.